So our first presenters are from Merck Co. and Tetra Science. Our first presenter is Wes Schaefer. He's a director of business and technology analysis in the composition of matter product line. Also presenting will be Evan Anderson, who's a manager at data architects at Tetra Science, and also Vinny Antonucci, who a lot of you may know. Vinny is the chair emeritus of Allotrope Foundation, and in his day job is also the composition of matter product line lead at Merck and Company. And so with that, we'll go ahead and turn that over to Wes.
Thank you. So thanks, Corey. Evan and I are going to talk about an ASM project at Merck that we've just kicked off. We'll talk mainly about the scope of the project, but we'll also go into some of the initial work that we've already began. Right. So this is a now well-articulated problem statement, and it's core to Allotrope's mission. In general, we have a diverse instrument landscape that includes simple IoT-based instruments, file-based instruments, and multi-system or database-linked instruments. Most analyses that we do are supported by multiple vendors. All of those vendors have their own proprietary data formats, and often the same vendor will have multiple formats itself. If you add to that what is often a very ad hoc data storage paradigm, with data stored locally on instrument computers, on various network shares, in the cloud, and in enterprise data content management systems, you see that we have a very heterogeneous environment. And all of this heterogeneity inhibits the data mining and the knowledge management that our industry needs to support innovation and streamline development, because of the effort needed to find, scrub, and standardize this data after the fact, so after it's been produced. Downstream systems also need to maintain multiple integration points for these diverse data formats and storage locations. And this is a situation that's proven to be not sustainable for the bulk of our instrument base, requiring manual data entry and manual review in many of our workflows. So the solution to the problem is to adopt a fair enterprise strategy. And how do we do that? We're going to transform our core analytical instrument data into standardized vendor-neutral format in a common cloud location, and we hope to have that completed by 2024. And then the second step of that is to connect that data with connect the instrument data with its contextual data that's stored in our notebooks, our LIMS, etc. That's not part of this particular project. We're focusing on the first part of this project. So most of us are familiar with the FAIR data principles: findable, interoperable, accessible, and reusable. In general, the findable and accessible parts are conceptually pretty easy. They can be practically difficult to implement, but there are ways to do that. The interoperable and the reusable data parts are much harder, and those are best done with standards. Standard data formats, standard models, and standard ontologies to interpret that data in those formats and models. And then finally, the common location. The primary use cases that we have for here, the first one is just a simple and consistent means of finding individual pieces of instrument data. So being able to search based on sample information, run times, instrument identifiers, key results, etc. The second use case is to provide an automated and efficient instrument data exchange with some of our downstream systems, such as our electronic notebooks and LIMS. And the reason we want to and the reason we want to do that is we want to lower the bar or the cost of integration, giving us the ability to decrease this manual data and manual review that we talked about earlier. And finally, the last use case is the ability to query across all of the data, right? So not querying for an individual piece of instrument data, but across all of the data for a particular instrument type, but also just search across all of the various instrument techniques and instruments for data applying to a particular sample or compound. Okay, so our initial solution approach has two important steps. The first one is the actual data transformation into the standard models and format, which is the ASM. And then the second part is this common storage location. Both of these facilitate the fair data concepts. Initially, we'll be converting our chromatography data because that's by far the largest segment of our instrument data. And we'll be doing that using the Tetra Science pipelines that Evan will describe later. Then we use our downstream applications to link to the relevant instrument data in this centralized cloud storage that we'll have. And then we'll also provide enterprise search platforms for within and across the various instrument types. So the third use case that we just talked about. Now we'll talk a little bit about what we've been doing initially. So just to give you an idea of the scope, so the strategy by the numbers, this slide is entitled. If we apply the 80-20 rule to our instrument inventory, the initial scope of our project is about 11,000 instruments. And that corresponds to software with installed bases of 10 or more. So there's 10 or more instruments using this particular instrument software. Those 11,000 instruments require 400 instrument software specific converters that will transform the instrument data into one of the 35 technique-based ASM models. So we're lowering the number of data formats that we have to support by an order of magnitude. And that means that our query tools and our downstream applications need to understand, roughly 35 versus 400 different integration points, assuming all of that data for a particular instrument type is in the same location. So this is really about simplifying how we can access our data. And then just sort of as a side note, it's interesting, if we do cover the last 20% of our instrument inventory, that's going to require an additional 1,800 different transformations. So as I said earlier, we're concentrating on chromatography because that's where the bulk of our instrumentation is. Those models already exist. The ASM models already exist. That's another reason we decided to start out with chromatography. And then this basically shows everything that our instrument inventory would require. There are already ASM models for 22 of what we're trying to do. We're working on 4 models for the end of this year or the beginning of 2023, and then there are additional 7 instrument types that we would need to have addressed through ASM. Let's just take a brief minute, since it's the first talk, for a brief review of the ASM. So one of the first things that I think is important is that it's ontology based, right? It's based on the AFO. So we're retaining the ability to do semantic reasoning on our data. It's a standardized JSON format supported by most programming platforms. So it simplifies integration points in that respect as well. And also, not only does the ASM standardize data, all the data from particular instruments for a particular instrument technique, but also common concepts such as sample information, device information, etc. That's also standardized across all the models, making these wide queries across all of our instrument base easier to do. So as we're looking at the ASMs, one question that came up is, how do we include some additional information that our use cases might require? And the ASM approach supports that as it is now, but it is a consensus-based minimalistic approach. So there will be times when we probably want to add additional data to that. There are three things that we can do if our use case requires us to capture more data in ASM. We can, of course, request changes to the ASM to add additional information. And I think we've done that in one or two cases. We can use existing or new AFO terms in the ASM and just provide the data using the ASM as is. The ASM supports that. But of course, it won't validate that data. It's not going to be part of the ASM manifest. And then the last step that we could do is we could then, if we do want all of that additional data validated, we would create a supplemental Merck JSON schema that we would validate the data against in addition to, not instead of, the ASM validation. Okay. Now we'll pivot just a bit, and we'll have Evan describe how Tetra Science is doing the actual data transformation.
Awesome. Thanks, Wes. So yeah, I'm going to take this opportunity to dive into the technical architecture for how we're leveraging TDP, the Tetra data platform, for data ingestion and transformation into ASM. So I'm going to start on the left here with this, with the instruments that are mentioned here. As you can see, we have a mix of plate readers, spectrophotometers, and chromatography data, including ChemStation, Thermo Fisher Chameleon, Cytiva Unicorn, and Waters and Power. Broadly speaking, we're taking two approaches for bringing this data into the platform. One is for file-based agents. We're leveraging the Tetra file log agent, which monitors a given set of directories for new or modified files to be able to bring those into the Tetra data platform. Below, we have our software-based integrations. These leverage unique software-based agents. So in this case, a Chameleon agent, Empower agent, and Unicorn agent to be able to detect new or modified injections on those software systems to bring them into TDP. These data coming into the Tetra data platform are routed using a central Linux-based hub to facilitate communication between these on-prem systems in the cloud. Once these primary data make it into TDP, they're saved in S3 under the hood, and they trigger event-based Python parsers, Dockerized Python parsers that convert the primary data into our intermediate data schema format, IDS. This is a JSON-based format that we have developed schemas for that we've developed schemas for a variety of instrument models. The next step here is once that IDS is saved back to the data lake, we map the IDS to the appropriate ASM. This happens in a couple steps. One is based off of the data that's coming in, we will route it to the appropriate modality based off of the content of the data. So one example is going to be Empower data could be gas chromatography model or liquid chromatography model. And the next is mapping that structured IDS data into the structured ASM. Thirdly, within that pipeline, we validate that ASM instance against the ASM schema. And finally, that ASM is saved to the data lake. Now, with that data saved in TDP, there are a few options for getting it out. One, all of the data in TDP is accessible via REST API. And Elasticsearch documents are generated for all the files in TDP, so you can leverage Elasticsearch to be able to search on that data. Secondly, data that's been transformed into IDS is accessible via SQL, and the metadata surrounding that data is also available via SQL. Thirdly, our Python pipeline architecture can be leveraged to send the data out to different locations. Exactly how we're going to leverage these different options at Merck is something that's subject to exploration at this point. So I think with that, we can move to the next page. This is a pretty busy workflow, but suffice it to say that onboarding so many instruments into ASM is a pretty collaborative effort. We've identified, so I guess the first place that this starts for us in order to try to hit time to value is leveraging existing primary data to IDS parsers to achieve structured data, right? So if the IDS exists, we're going to follow that yes into, is the ASM available? Now, if the ASM is available, then it's a pretty simple operation. We map the data to ASM. We create this IDS to ASM pipeline, which is just a mapping JSON to JSON, and do validation. One thing that's missing is that in this is if the IDS has more terms than the ASM, then we might bring this to the working group as Wes mentioned. Now, if an ASM isn't available, it's similar to the situation where there might be terms we want to add. At that point, I'm not going to get into all the nuance here. Suffice it to say that we would start to be able to suggest a new model to bring to the working group based off of the information that we have on the different IDSs that we've developed for that given instrument class. Now, in the situation that no IDS exists, but ASMs are available, then we can take more of a direct primary data to the most minimal terms to ASM approach. Yeah, so I think that is, so we've kind of theorized these different options. In our first approach here, we're really looking at models that are already developed and IDS that are already developed, and really looking forward to collaborating on where we can contribute to either ASM terms that we could propose, or even potentially ASMs that might be proposed through the working group. And with that, speaking of collaboration, Wes, I think it's back off to you to talk about the roles on our team.
Great, thanks, Evan. Yeah, so we knew that to be successful, we would have to have a strong partnership of scientists, the data scientists, and IT resources. And along with that is a clear definition of the roles and responsibilities. So this is a rather busy slide, but we thought it was important to show you how this is going about. And one of the other things that came back to us from our business area was, please be mindful of the scientific SME's time. Their day job is to do chemistry, biology, etc. So just leverage their time wisely. So for the chromatography data, we're using the following roles. First, we're using internal Merck data scientists and the Tetra Science team to actually map out the ASM conversion and engaging Allotrope whenever there are issues or missing terms, etc. And then finally, we're also then engaging a dedicated internal deployment team to deploy and perform the qualification testing of the instrument pipeline. So also then limiting the amount of time required from the instrument owners. So everything that we've done here is to make sure that the time that we spend with our scientific SMEs is needed, but when it is needed, that we actually get that support. So that's the agreement that we have with our business areas, and how we're leveraging internal IT resources and external IT resources in terms of deployment to move this project along. Okay. So now in summary, to verify the new verb, I guess, that's out there now, it's instrument data. Merck is implementing ASM at scale. This is a 2.5-year project that will encompass about 11,000 analytical instruments. We've just gotten started, and we'll report back out in the spring as to how things are going, and also we'll be doing it continuously through the Allotrope working groups. some of the allergens, of course, Ben and Anon at Allotrope. Oh, looks like this skill got a little messed up, but our internal data modeling group. Merck SMEs that are way too numerous to mention, but here are some of the key SMEs that we have for chromatography. The Merck Tetra Science deployment team, and then of course our Tetra Science partners themselves. And with that, we would be open for some questions.
Great, thanks Wes and Evan.